Hello everyone from Math 1340, Statistics. It's Professor Wenson here again with another video on your KnewtonAlta homework titled Section 3.1 Part 1, Terminology. And this is terminology specifically related to the topic of probability. We're going to be calculating the probability of a certain event occurring. And this section here is just an introduction to this and a lot of definitions, a lot of terminology. Alright, so here I am in the, hopefully you recognize what the KnewtonAlta homework looks like by now. I'm in a preview of it, right? So like I've been saying every video, what I see, the exact questions I see and the order of the questions I get are not going to be the exact same questions or the exact same order that you're going to see them when you do the assignment. It's different for every student. But the objectives are the same. And the types of questions are the same, and the way you would do them, the way you would work through them, is the same. So hopefully this video is a good, you can use it as a nice guide to help you through this assignment when you do it yourself. Alright, so again, you have the title of the section, the homework assignment here, the mastery bar telling you how far along you've gone, and you can look at all the objectives and your progress in the objectives. Alright, right now this question here is on the objective, define and explain probability terminology, likelihood, and experiments. Right. So as I've been saying, usually the first time I see an objective, I would recommend to you to, again, unless you've done the reading and you feel comfortable, right? If you read your section 3.1 in the OpenStax statistics book, or you watched the videos in my Canvas page for section 3.1, if you did all that and took notes and organized things and practiced some stuff ahead of time, and you feel comfortable with the terminology, then you can go ahead and answer questions right now. But if you're still uncomfortable, I'd say click on More Instruction every time you see an objective for the first time. So I'm going to do that. More Instruction, View Instruction. All right, now I'll read some of these to you, and we'll go into some practice problems. So some basic probability definitions. So whether we think about it or not, probability surrounds us every day. We may ask ourselves, what is the chance that it's going to rain today? Or think, the flights to Los Angeles are always late. I wonder if I should expect my LA flight to be on time today. We are comparing what we know of an event occurring to inform our expectations about the future of similar events occurring. This is probability, right? What's the likelihood that this will happen in the future? So in this section, we will introduce some of the basic language we use to talk about probability and give examples of how to use this terminology to help us solve probability problems. All right, so the first three definitions are on experiments, trials, and outcomes. An experiment is a planned operation carried out under controlled conditions. For example, flipping a coin twice, right, is an example of an experiment. So I just flip a coin twice, record my results. A trial is one repetition or instance of an experiment that is being repeated multiple times. So if you take this example from earlier, for example, take the experiment of flipping a coin twice. If this experiment is repeated 3 times, then each trial consists of flipping a coin twice. There are 3 trials total. Right, so basically if I flip the coin twice, recorded my data, I got heads, that's 1 trial. Then I flip the coin twice again, right? I repeat the experiment. Every repetition of the experiment is called a new trial. So I flip the coin twice again, record my results, tails, heads maybe, and then I flip the coin twice again, right? The 3rd trial of the experiment, and record my results. An outcome of an experiment in probability is any of the possible results. Right, and we're going to make lists of outcomes. For example, in this flipping a coin, if we are flipping a coin once, the outcomes are simply heads and tails, right? You could abbreviate them H and T. For a more complex example, right, that experiment with the flipping the coin twice earlier, right? Consider the experiment of flipping a coin twice. In this case, the outcomes are every possible combination of heads and tails, when you flip the coin twice. So you can get two heads, a heads on the first flip, a tails on the second, or a tails on the first flip, a heads on the second flip, or two tails. So here is a list of, all the possible outcomes for that experiment, the experiment of flipping a coin twice. So their first example, and we'll get the problems later as well. So a question is, see here, there's two friends sit down together to study in the library. One of the friends is a nursing major, and one of the friends is a business major. You choose one of these friends at random to receive a free coffee from the library cafe. So the experiment here is choosing a friend. Right, what are you doing? I'm choosing one of these two friends, choosing a friend at random. How many trials does this experiment have? They didn't mention anything about doing it more than once. Right? They just said you choose one of these friends and give them a free coffee. So this experiment is only run one time. There is one trial in the experiment. And what are the possible outcomes of this experiment? Well, one of the outcomes is I chose my nursing major friend, and then the other outcome would be I chose the business major friend. Right? So there are two possible results. Right? Here you can choose either from the nursing major or the business major. Hopefully that is a nice example as to how to apply these words, what these words experiment, trial, and outcome mean, and we'll see more later. Probably with this question here, right? When I hit continue, they'll probably ask me a very similar question. So each side of a fair six-sided die has a certain number of dots on it. 1, 2, 3, 4, 5, or 6. The die is rolled by a board game player as part of their turn. Identify the correct experiment, trial, and outcome below. So you're selecting multiple things here. The first two relate to the experiment, the second two relate to the trial, and the third two relate to outcomes. All right. So I would say, the experiment here, what's being done by the player, is just the rolling of the die. Right. Let's see, is identifying the number that is rolled on the die, or is rolling the die? I mean, the die is rolled by the player. They mention roll in both of these, but then you also want to identify the number. I would say that rolling the die and recording the number would be the experiment here. So I'm going to select that one. Because just rolling the die, I don't know, you also look at the number after you roll it, right? Identifying the number that roll. I would say that this is the experiment being performed. A trial is one rolling of the die, just doing it one time. Every time I roll the die, that's a new trial. So maybe that. And then the outcome is the number that is rolled on the die. All right, so maybe the experiment, because they do talk about the number here, perhaps then the experiment is just the roll, and then identifying the number is the outcome. Because, again, the rolling of the die is a trial, what the person's doing. So I'm going to say the experiment is rolling the die. A trial is one rolling of the die, and the outcome is the number that appears. Right. And yes, okay. So yeah, because they mentioned the number at the end being the outcome. I'd say that just rolling the die is the experiment. I roll a die, and that's one trial. I roll it again, another trial. I roll it again, another trial, and each time there is a different outcome. I rolled a 1, and then a 3, and then a 6, whatever. Okay. Wonderful. And again, they do the explanation here. So next is some more definitions, right? So aside from experiment, trial, and outcome, we have sample space, events, probability, and likelihood. All right, so when conducting a random experiment, it is desirable to know the possible outcomes of the experiment and the chance with which they will occur. This is where the idea of probability comes in. All right, so a sample space is the set of all possible outcomes of an experiment. So they give an example here. If you flip a fair coin, the possible outcomes are heads, H, and tails, T. So the sample space is this set, right? It's a set. So you see how they have the little curly braces here? It's a set, a collection of outcomes, all possible outcomes. So for flipping a coin once, you can get a head or a tail, and that's it. That would be considered the sample space for that experiment. So yeah, notice that the convention is to write the sample space in set notation, right, with the curly braces. An event is some subset of the sample space, right? So the sample space has all the possible outcomes in it. An event has some collection of outcomes, not necessarily all of them, right, of an experiment. So an event is some subset of the sample space or some grouping of possible outcomes of an experiment. Typically, we use capital letters to represent events like A or B, capital A or capital B. An event of flipping a coin would be flipping a heads. So if I said, what's the probability of this event? Well, we'll talk about probability here in a second. But an event is just a collection of outcomes, possible outcomes, not necessarily all of them. Probability is a measure of a particular event happening compared to all events in a sample space. For example, the probability of flipping a heads on a fair coin would be 1 out of 2. Because again, there's one head. You can flip a head. There's one head out of the 2 possible outcomes, heads or tails. All right, there is one particular event that we are interested in, flipping a heads, compared to 2 events in the sample space, heads or tails. Right, so 1 out of 2, 1/2, 50%, 0.5. You can write it in all these ways. Probability can be described using fractions, decimals, or percents. And probabilities, this is key here too. Please remember this. Probabilities are always going to be from 0 to 1. Never bigger than 1, never less than 0. So you're never going to have a negative probability. Or from, if you're writing percentages, from 0 to 100%. But you'll never have a probability greater than 100% or less than 0%. Right. And then finally here, the likelihood of a probability is an interpretation of how likely an event is to occur. So this notation here with the P, the capital P, and then in parentheses you have capital A here, this is the probability of event A. All right, so when you see this capital P in front of parentheses like this is probability. So what's the probability of event A occurring? And if I say that the probability of event A occurring equals 0, that means that event A is impossible. It can never happen. On the other hand, if I say the probability of event A equals 1, that means that event A will always happen. Right? It is guaranteed to occur. And then you have stuff in between, like the probability of flipping a heads earlier. The probability of an event A is equal to a half. 0.5 means that the event A is equally likely to occur or not occur, right? You have a 50-50 chance, 50% chance. You might have heard that kind of stuff before. Right? But please, again, know that probability will never be greater than 1, and it will never be less than 0. It's always going to be some number from 0 to 1, or 0 to 100%. All right, so they have an example here. So a fair coin is flipped twice. What would be the sample space? Now again, the sample space is a description of all possible outcomes. So this was mentioned earlier in the video, right? When you flip a coin twice, you have possible outcomes of 2 tails, or a tails then a head, or a heads then a tail, or 2 heads. 4 possible outcomes. Okay. They describe that here. So now here, suppose the event A of getting a heads on the second coin flip. What outcomes would be in this event? Remember, an event, it's like the sample space, all right, but not all of them necessarily. Right? The sample space is also an event, but it's the event with all the outcomes. Other events like this would have just a few of them. So you see down here, event A, the event of getting heads on the second flip of the coin, is this collection with just heads, heads, and then tails, heads. See, there's a heads on the second flip. And that's it, just those 2. All right, then what would be the probability of event A, right? The P of A here. Well, there were 2 outcomes in event A out of the 4 possible outcomes in the sample space. So 2 out of 4, or reduce that to 1 out of 2, 1/2, 50%. Right? There were 2. 2 is the number of times we can have heads on the second flip, divided by 4, the total number of elements in the sample space. All right. So another way of saying this is the probability of an event is the number of ways that event can happen divided by the total number of possible outcomes. Right. Or in the numerator, you have the number of outcomes in the event, and then in the denominator, you have the number of outcomes, total outcomes in the sample space. And then what's the likelihood of event A? Right? If the probability of A is a half, we would say that event A is equally likely to occur or not occur. Right? There's a 50-50 chance. It is not closer to 1 or 0, but rather exactly in the middle. Right? So if a probability is closer to 1, that means that it's more likely to occur than it is not to occur. And if a probability is closer to 0, that means it's more likely to not occur than it is to occur. All right, again, some key terms. I've already read these to you. Let's continue on with a problem hopefully related to these new definitions. All right, so here, question is, there are 150 new employees at a tech company in Southern California. 30 new employees are randomly assigned to each orientation group, A, B, C, D, and E. All right. Identify the numbers of each of the following. All right. So how many people are in the, again, what's happening here is these 150 employees are going to be broken up into 5 groups. A, B, C, D, and E. And each, if it's 150 divided by 5 is 30. So each group is going to have 30 employees. But they're doing this randomly, right? So, for group A, they'll pick 30 people at random. Then for group B, they'll pick another 30 people at random. And then another for C, D, and E. So the experiment here is this selection of employees to go in these groups. Right. So what's the sample space? Right, how many new employees are, basically that's like the population, right? Everyone. There are 150 new employees at this company, right? And in each event, right? Say each group represents an event. You can either go to A, B, C, D, or E. There are 30 employees in each of these groups. And so the probability of being in, say, group C, right? This is the probability that you choose a new employee that has been assigned to orientation group C would be, well, how many, again, the numerator would be how many employees are in group C. So you can go 30 out of, and then how many employees are there total, right? What's the sample space, total possible outcomes. Now you could write this, and I don't know if it'll take it this way. I'm not going to try, because I'm gonna suggest to you that you reduce your fractions. You see, 30 out of 150 is totally fine for the probability of picking an employee from group C. But 30 out of 150 reduces to 1/5, right? 1 out of 5, which makes sense, hopefully, because if you're picking an employee, there's only 5 possible groups they could be in. The sample space would have these 5 groups, and C is one of them, and they're equally spaced. They're equally broken up into 30 in each. So you'd have a 20% chance, or 1/5 probability of being in group C. And that's correct. And again, they go into the 30 out of 150, but reducing it to 1/5, right? Talk about that down here. So again, I think they're expecting you to reduce your fractions. So please do, unless they say otherwise, right? Unless there's some problem where if you read the instructions, they say, just don't worry about it. They might have that in some of these. All right, another question related to this: flights from Miami for New York City are delayed 27% of the time. So how likely is it that a particular travel's flight from Miami to New York will be delayed? Well, the probability of being delayed is 27%. That's less than 50, which is closer to 0, right? So the probability of being delayed is closer to 0 than it is to 1. So the probability is, now it's not that close to 0. It's not that close to 0, but it is closer to 0 than it is to 1. It's not equally likely. The probability is not a half, right? It's not 50%. So I'd say somewhat unlikely that the flight's delayed, because again, the probability is closer to 0 than it is to 1. The probability of the flight's being delayed. Saying that the probability is close to 0, close to 0 we'll usually consider to be maybe like 5% or 1%, really close to 0, not 27%. Right? So I'd say it's somewhat unlikely that the particular traveler's flight would be delayed, because the probability is closer to 0 than it is to 1. Hopefully that made sense. Right. So now I'm in a new objective. Now we've talked about events, right? Remember, an event is just a collection of outcomes of an experiment, possible, some possible outcomes. Now we're going to create what are called compound events, where you're kind of taking 2 events and combining them with some words, or just one event with the word not. So you got the word and to combine 2 events, the word or to combine 2 events, or the word not on 1 event. All right, so we're going to use and, or, and not notation to describe new events. So again, first time I'm seeing this, so I'll go to the more instruction for you. And again, it's another one where I'll read some of this. So using or, and not to describe events. So in probability and statistics, and you've probably seen these words or and also used in algebra with inequalities. Remember, there were inequalities, compound inequalities connected by the word or the word and. So if you remember how those worked, this should be pretty simple. We often are interested in combinations of events, or compound events. Below, we give some examples, some of the combinations that are of particular interest. You will eventually learn formulas, not this section, but later. You will eventually learn formulas to compute the probabilities of these combinations of events. For now, we are interested in just simply describing events with this notation. Right. So an outcome is in the event A or B, if the outcome is in A, or the outcome is in B, or it is in both A and B. This can be represented by a Venn diagram as shown below. Now, a Venn diagram, just a picture, you got this big box here represents everything. See, usually the U represents the universal set, or everything possible. And then some circles or ovals will represent events. This like blue circle here represents event A. So everything inside the blue circle is part of event A, and then the red circle or orange circle represents event B. So all the values, all these outcomes inside the red circle are in event B. So you have 1, 4, 3, 5, 10, those are in event A. 12, 3, 5, 10 are all in event B. So in the union, this is called the union, by the way, they bring that down here. A or B, if you talk about the event A or B, it just includes everything that's in event A or in event B or both. So 1, 4, 3, 5, 10, and 12, all of these would belong to the event A or B, and they go this, I'll explain it again here. So here we see A represented by the blue circle, and notice that A is the set of outcomes 1, 3, 4, 5, 10. B is represented by the orange circle, and B is the set of outcomes 3, 5, 10, 12. A or B is then the set with 1, 3, 4, 5, 10, and 12 in it, right? Because it's all the stuff that's either in A or in B or in both. Very inclusive. All of the numbers found in event A or event B. Notice that 3, 5, and 10 are each listed once, right? Even though they appear in both A and B. So no need to repeat yourself. Right? And as I mentioned, it's sometimes referred to as the union of two sets. So A or B may be symbolized sometimes as A union B with this like with this U looking shape. You see this U shape between two events that represents the word or the union of two sets. Okay. All right. And events. All right. An outcome is in the event A and B if the outcome is only in both A and B at the same time. All right. So again, same Venn diagram here, same picture. So if I was asking you about the event A and B, the only outcomes that would be in both of them at the same time are 3, 5, and 10. Right, the 1, the 4, and the 12 are not in the overlap. They don't belong to both. So we see that A equals the set 1, 3, 4, 5, 10. B is the event with 3, 5, 10, and 12 in it. A and B is just like I said, the event with 3, 5, and 10 in it. Right, because those are the only ones that are in both A and B at the same time. All right. Now, an AND event is symbolized by this upside down U symbol. So if you see A and B, or this A with the upside down U symbol between A and B, that means the same thing as A and B, and it's called the intersection of the two events. And hopefully that name makes sense when you look at the Venn diagram. It's like what outcomes are where they overlap, where the events intersect. Right. And finally, you have the word not. All right, so the complement, right, the complement of event A is denoted by A prime. It's A with an apostrophe, read A prime. Now in this book, it's A with an apostrophe. I've seen other books where it's A with a bar over it, or A with a little C above it for complement. But in this book, it's just A prime or A apostrophe. This A prime consists of all outcomes that are not in A. So you can think of A prime as not A. So it's all the outcomes that are not in A. So here, look at the same Venn diagram. The outcomes in A are 1, 3, 4, 5, and 10. All those are in A. The only outcome on this picture, and you look at the whole box, right? The only outcome that's not in A is 12. So you see again, A is 1, 3, 4, 5, 10. So not A, again, is just 12. The only outcome listed in this picture that's not in A, that's called the complement of A, or A prime. Right. So it's all the elements of the sample space U, right, the universal set, as I mentioned, that are not in A. And here's another way to write this too. You could say A prime. You also might see this little tilde, like a wavy line, right? It's called a tilde. Tilde A, again, that just means not A, not in A. All right, so an example. A deck of cards for a board game contains red cards numbered 1, 2, 3, and 4, and blue cards numbered 1, 2, and 3 as shown below. The cards are shuffled and placed face down on the game board. So they identify some events here. Let capital R be the event of drawing a red card. Capital B be the event of drawing a blue card. And capital E be the event of drawing an even numbered card, right? So 2 or 4, right? There's only even numbers are 2 and 4 here. So it says use and, or, and not to describe the following events. So drawing a blue 2. So that would be blue and 2 at the same time, right? To be the blue 2 card. So that's B and E, right? Blue and even. So you see B and E, or B intersect E. Drawing a red 1. That's a card that is both red and the number 1 at the same time. So it's R and odd. Well, odd is not even. So R and not E. R and E prime. So part B. Now again, there's multiple ways you can express the same thing, but blue and even, R and not E. All right. Yeah, so there it is. Right. R and not E, right? For part B. Part C, drawing an odd card is just simply not E. That simple. Right, just not E. And they go through a whole thing where you can describe it in many other ways, but not gonna do all that. All right. And here's another example. I'll get to a problem like this in a minute. All right. So hopefully you know what the words and, or, and not represent, or what they mean. All right. So for example, a standard 6-sided die shows a number 1, 2, 3, 4, 5, 6 on each of its sides. You roll the die once. Let E be the event of rolling the die and it showing an even number on top, right? So you roll an even number, 2, 4, or 6. And the capital L represents the event of rolling a number less than 4. Now, a number less than 4 would be 3, 2, or 1. Right. Rolling a 3 is an outcome of which of the following events? All right, so I'm going to go to bring up a piece of paper here, and we're going to show you. I'll write out what these events are. Right. So we have this event E, as mentioned. All right, E is rolling an even number. So that event contains the outcomes of 2, 4, and 6. Right. Then event L. Right, event L is rolling a number less than 4. So that would be the set with these outcomes, 1, 2, and 3. Right. And then you have the sample space. Right. The sample space is the list of all possible outcomes. Now again, they've been representing that on the Venn diagrams with the capital letter U for universal set. Maybe I'll put a little things on top to make it look special. The sample space is this one. You know, when you roll a die once, all the possible outcomes are 1, 2, 3, 4, 5, and 6 as they mention. Okay. Now, I could make a little Venn diagram with these as well. All right, here's again, this represents the universal set, the sample space. Then I have, say, event E here has 2, 4, and 6. Right, so here's I'll say this circle represents event E, and you got another one for event L. All right, 1, 2, and 3. Notice they do have some overlap, right? They do share an outcome of 2, so I will draw them so that they overlap. You know, if they didn't share anything, I wouldn't overlap them. Right? I'd just draw a separate circle somewhere else, but they do overlap. All right, so here's L. Right? Okay, and then I'll list the outcomes. Right? We have 2. Oh, sorry. 2 should be in the overlap. Right? They both have 2. Right? So there's 2. And then 4 and 6 aren't in L. So there's 4 and 6, and 1 and 3 aren't in E. They're in L though. So 1 and 3 are over here. And this takes care of every possible outcome except 5, right? So 5 I'll put out here isn't in either of them. All right, so 1, 2, 3 are in L, and then 4 and 6 and 2 are in E, and 5 is in neither of them. Okay, so hopefully this picture is clear, if hopefully it's not too small. All right, now what we're looking at here, and I'll run through these. They want me to give, let me blow this up a bit. Let me take it to the big screen. So the first thing they want from me is they're saying, I'll go through these. E, what is this event? E or L. Right, E or L. Remember this or. This is the union. So this contains everything that's in E or in L or both. So everything but 5. Right, 1, 2, 3. Those are in L. 4 is in E. 5 is in neither of them, and 6 is in E. Right. So this does contain the number 3. All right, so I'll check that box off later. The next one is not E and L. All right, so if this is E, then not E, okay, not E. Remember, not an event is everything in the sample space that isn't in that event. So everything in U here, everything in the whole box. So that isn't an E. So 1, 3, and 5, right? All the events here, the only ones that aren't in E are 1, 3, and 5. So not E is the set of odd numbers, right? Because remember, E was the set of even numbers, so not E would be the set of odd numbers. I'll also put not L. Right? Now L was the numbers less than 4. Not L would be the numbers greater than or equal to 4, 4, 5, and 6. Right? These are the numbers in the universal set that are not in L. So here, not E and L is the set of events that are in both not E and L at the same time. So what do these two share? Well, they both have a 1 and they both have a 3. So this is the set with outcomes 1 and 3. So this also has 3. So I'll check that one. How about just E and L? Again, this is and, so you're looking for overlap, intersection. Looking at E and L, what do these share? Just the number 2, just the outcome 2. All right, so this one doesn't have a 3 in it, so I'm not going to check that one. Then they want not E or L, or not L, sorry. not E or not L. So I'm looking at the not E, not L, and then or is again just the union. So what's in E, what's in not E, or what's in not L, or both. So we got one, just basically no two, right? Got one, got three in one of these, got four, got five, and got six, right? The only number that's not in here is the number 2. Right? So 3's in this one as well. How about not L? Well, I already wrote not L. It's up here. Doesn't have a 3 in it, so I'm not going to check the alpha. And then the last one I'm looking at is E and not L. Right, so you look at event E, event not L, and do they have anything in common? Yeah, the 4 and the 6. So 4 and 6 would be in that set. All right. But again, not the number 3. So E or L has 3, not E and L has 3, and not E or not L has 3. And so those will be the only ones I check off back in the assignment. So I said E or L has 3, not E and L has 3, and not E or not L has 3. And the other 3 don't have the number 3 in it. All right, and I'll submit, get rid of this. Great. All right. So yeah, I would recommend doing that, making a list. What are these sets? Maybe writing out the sample space, the list of all possible outcomes, and making a list of outcomes that are in each of these events. Okay. Right, so this one. Now this one's one of those interactive ones where you have to move the dots and to move them to the correct place on the Venn diagram. All right. So here, this is a little different question. It says two fair dice are rolled. One blue, abbreviated B, and one red, abbreviated R. Each die has one of the numbers 1 through 6 on each of its faces, right? It's a regular die, 6-sided die. The dots in the Venn diagram below show the number and color of the dice. So let A be the event of rolling an even number on either of the dice. Let B be the event of rolling a number greater than 4, so 5 or 6, right? Just greater than 4 on either of the dice. Move the dots on the Venn diagram to place the dots in the correct event A, B, or A and B, the overlap. Notice that you might not use all the dots, right? So let's see, rolling an even number means rolling a 2, a 4, or a 6. So anything with 2 attached, so like B2, goes in there, right? Now the overlap is rolling even and greater than 4. So rolling an even number and a number greater than 4 is just rolling 6. So anything with 6 attached, like the B6, rolling the blue 6 goes in the overlap. The red 6 would go in the overlap. Right? And that's it, right? You get the blue. You either roll blue. Those are the only ones with 6s, right? An even number that is also greater than 4. So I'll keep putting the other evens over here, right? Rolling the blue 4, that's rolling an even. The red 4 and the red 2, right? Those are rolling even numbers. Okay. Then over in this area is where I roll numbers just greater than 4. So now I already put the 6s in here because those are also even, right? Where the overlap is. So the 5s, right? Anything with a 5, the blue 5. The red 5, and that would be it, right? All these ones out here don't belong to anything, right? Because red 3, red 1, blue 3, blue 1, those don't have even number rolls, and they don't have rolls greater than 4, right? So that's it. That's what they meant by move the dots into the correct places in the Venn diagram. So hopefully that's not too bad when you come across it. Just pay attention to the events, right? They're gonna, you might have your events might be described in some different way. Okay, now we're back to a question about the the terminologies. So again, here, doctors at a research hospital are conducting a study to see if flu patients received a flu vaccine in the past year. To collect their data, they ask each person treated for the flu for the flu at their hospital, whether they received the vaccination. So the experiment here is just, asking whether a flu patient received the vaccine. Right? That's what they're doing to collect the data. And each person they ask is a different trial. Right? So they ask one person, that's one trial, ask another person, that's another trial. So it's asking one patient if they've been vaccinated. And then the outcomes are, an outcome would be either yes or no, right? It says an outcome, right? All the outcomes are just simply yes or no, right, when they're being asked. Okay, so done with that one. All right, back to the and, or not notation. So again, a deck of cards contains red cards numbered 1 and 2, and blue cards numbered 1, 2, and 3. So R is the event of drawing a red card. B is the event of drawing a blue card. E is the event of drawing an even numbered card. And O is the event of drawing an odd numbered card. Right. So which of the following events includes the outcome of drawing a blue 1? So that's blue and odd at the same time. So blue and odd. But let's see, red and odd? No, that's not red and odd. Blue or even? Well, yes, remember, or means it's an either one. So did I draw a blue card or an even numbered card? Well, yeah, I drew a blue card. So blue 1 would be in that event. Red or even? Well, neither of these happen, right? Blue and odd. So this is not going to contain the blue 1. Blue and even. Remember, the and means they both have to happen. So I got the blue, but it's not even. So not this one, right? I already said blue and odd. And red and even, no way. Right, so just these two events would have the blue 1 in it. Okay. So just again, remembering what and or means. So one more here on the use of and, or, and not. All right, so another one with the moving dots around. Okay. So different types of advertising methods are being considered for a company's new product. A magazine ad, labeled M, a television ad, labeled T, a newspaper coupon, labeled N, a radio ad, labeled R, a coupon mailer, labeled C, and a social media ad, labeled S. The coupons are both good for $10 off the item. The dots in the Venn diagram below show the various methods, right? All these ones with the labels, all these labels up here. An advertising specialist considers a method at random to review. All right, so let capital A be the event of selecting a method that gives a discount, and B be the event of selecting a printed method. Right. So so reading through here, right? It says the coupons are good for discounts. So we have a coupon mailer and a newspaper coupon. Right? There's only 2 coupons, right? The coupons are both good for $10 off. So the ones that say coupon, newspaper coupon, so the N gives a discount, and the coupon mailer C gives a discount. So in this discount area, I'm going to make sure that N and C are in there. That's the event A. And then event B is printed, right? A printed method. So like, magazine would be printed. Television's not printed, right? It's not on paper. A newspaper coupon would be printed. A radio ad is not on print. A coupon mailer would also be printed, right? It's something that gets mailed, right? A social media ad is not printed, right? It's on your computer, right? So the ones that give discounts are the newspaper coupon, which is both giving a discount and on paper. So I'm going to put both. I'm going to put in the overlap. Same thing for the C, the coupon mailer. It's being mailed out, it's on paper, it's printed, and it gives a discount. Right? And those are the only two ones that should be in that discount box, the discount circle. Now, the rest of them, S was the social media ad. That's not printed. I'm going to leave that. It doesn't give a discount. Right? The only two that give a discount are the newspaper ad and the coupon mailer. Let's see. T was television ad, which is, again, neither printed nor giving a discount. M was magazine, which is printed. That's on paper, but doesn't give a discount. And R is radio, right, which, again, doesn't give a discount and is not printed. So based on reading all that, here's how I'd have my Venn diagram set up. Okay, and again, so that one you kind of would have to know what's on paper and what's not. So just read carefully and hopefully understand what they're asking you. All right. So I'm done with 2 of the 4 objectives. Let's see what the next new one is. Explain the role of probability in statistics. All right, so this has, I'll go to more instruction. Now there's a video here, I believe. I'm not going to watch the video within the video. All right. So you're looking at an example of how probability is used to make inferences in statistics. What I do want to talk about, though, is, remember, closer to 0 a probability is, the less likely the event is to occur. The closer to 1 a probability is, the more likely an event is to occur. So in this part here, this objective, you're going to see they're going to ask you questions about whether or not an event seems likely to occur. So would you suspect the event can happen in a few ways or many ways? Would the probability be closer to 0 or closer to 1 in your mind? So again here, which of the following events seem like they would be unlikely to occur, right, by chance? Select all that apply. So if you flipped a coin, now unlikely to occur, that means has a low probability. Now we're going to say unlikely to occur here is like a probability of, I'll say 5% or less, just something very small, very close to 0, very unlikely to happen. Right. So if I flipped a coin 100 times and having it land on heads 15 times, I'd say that would be pretty unlikely. You'd expect around 50, right? Because remember, flipping a coin, you got heads, tails, 50-50 shot at both. So you'd expect, and we'll talk much more about expected value or expected outcomes in later sections. But if you flipped a coin 100 times, you'd probably expect around 50 heads and 50 tails, right? I'm not saying you get exactly 50 heads and tails, but around that. So flipping a coin and getting 100 times and getting 15 heads is probably unlikely to happen by chance, because you'd expect more near 50. Right? Rolling a die, 6-sided die, 100 times, and having a 6 land face up 15 times. Okay, remember, every single value on a die has a 1 in 6 probability of showing up. Right? So I mean, a sixth of 100. Right, 1/6 of 100 is about 17. Right, 16, 17. So 15's around there. Right? I would expect the 6 to show up about 16, 17 times. 15's close to that. So I would think that this would be likely to happen. I would expect this to be something that would happen if I rolled a die 100 times. So I'm not going to do that one. How about randomly selecting 10 people out of a crowd and having them all have brown eyes? That's probably not going to happen, right? The chances of that happening, all 10 people you randomly select having brown eyes, that would be very slim in my opinion. So again, this is kind of an opinion thing. I mean, not really. I mean, there are correct responses here, but just think about them a little bit. Would you expect it to happen or not? I would not expect this to happen, so I'd say it's unlikely to occur. Guessing somebody's name correctly without having previously met the person, I would also think that would be unlikely to occur, right? Just again, what would seem unlikely to happen, and then you select them. Right? Have a low probability. Right, so same objective here. All right, so the question is, a standard roulette wheel with slots labeled 0, 0, 0, the double 0, right? 1 through 36. So there are 38 slots, is spun 60 times. Of these spins, the number 7 is spun 7 times. So you spin 60 times, and 7 shows up 7 out of those 60 times. Assuming the wheel is fair, the probability of this occurring by chance is very, very, very small. Do these results have statistical significance at the 1% level of significance? All right, this is something we're going to talk about a lot. All right. When they say an outcome has statistical significance at a certain level of significance, that means that the probability of that occurring is less than that number. All right. It's unlikely to happen, right? This result then does have statistical significance at this level. This is 1% level, because my probability is less than 1%. Right? If the probability of an event occurring is less than the percent significance level, this level of significance, then we'll say the results have statistical significance. Right? So yes, the probability of the results occurring is less than 0.01. Right? This probability is definitely less than 0.01. So they'd say that these results have statistical significance. This result is unlikely to occur on its own. Again, fancy words to kind of describe a pretty simple idea. All right, same thing here. A farmer claims that the average mass of an apple grown in his orchard is 100 grams. To test this claim, he measures the mass of 150 apples that are grown in his orchard and determines that the average mass per apple to be 98 grams. The results are calculated to be statistically significant at the 0.01 level. What is the interpretation? Right? When they say results are statistically significant at a certain level, that just means that the probability of what the farmer did occurring is less than 1%, or less than or equal to 1%. Very small, very unlikely to occur. So that means that the probability of him picking 150 apples and having their average be 98 grams, when he said that the average was 100 grams, the probability of that happening is less than 1%. So this means that So at the 1% level of significance, the mean mass of the apples grown in the farmer's orchard is different from 100 grams. At 1% level of significance, the mean mass of the apples grown is 98 grams. Now, so the farmer made the claim. Again, the farmer claims the mass is 100 grams. The average mass of the apples is 100 grams. But then he picks 150 apples and their average mass is 98 grams. And they're saying the probability of that occurring would be less than 1%. So we're going to the probability of that occurring, if the mass was truly 100 grams, the probability of this occurring is less than 1%. So the chances are the mass isn't 100 grams. Right, the chances are his claim was wrong. Again, that concept is going to be hopefully become much more clear when we get into chapters later on testing claims. We're going to get a claim from someone. You're going to assume that claim is true, and then take a sample and say, hey, if I assume the claim is true, and what is the probability of this sample? What is the probability of this outcome? And if that probability is small, if it's unlikely to occur, if it's statistically significant, however you want to say that, well, then the claim is probably wrong. Right? So that's what we're saying here. At the 1% significance level, the mean mass of the apples grown in the farmer's orchard must not be 100 grams then. if this is if this result happens, right? Having 150 apples with a mass of 98 grams each. Again, a lot. Hopefully that makes sense. And again, they read it down here, and you can go into more instruction. Again, there's more stuff on statistical significance and more instruction. All right. You know, in fact, I'll click on more instruction just to show you. There should be stuff on. Yeah, here we go. So we see probability used on a regular basis. Right? The purpose of probability models is to analyze samples, right? Sometimes very large samples, to make predictions about various types of populations. For example, blah, 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 right? They rely, statistical significance is mentioned here. So here's an example. Suppose you want to test whether a die is fair. Every outcome of a fair die is equally likely to occur, right? 1 through 6, with each possible outcome having a probability of 1/6. If you toss a die 120 times, and of those times you roll a 2 a total of 16 times, is the die unfair? No. Because you'd expect, remember I said each one you'd expect around 16, 17 times? If this is 120 times. Right, a sixth of that would be 20 times. This is close to 20. It's not that far off of 20. So if you rolled 120 times, you'd expect about 20 to be 2s. So 16 of them being 2s isn't that far off. So while we expect to see near 20 of the 120 die rolls to result in a 2 of this experiment, this does not mean that every time we roll a die 120 times that we roll a 2 exactly 20 times, right? We're expecting around that. In some experiments, we may roll a 2 more than 20 times. In others, we may roll less than 20 times. In another experiment, if you toss a die 600 times, right, you should get a roll of 2 around 100 times. However, let's say that in one experiment you roll a 2 160 times, which is very different from 100 that you would expected. So although it is possible that 160 rolls of 2 can happen, it is much more likely that the die is weighted in a way that makes 2 more likely to be rolled. Right. So again, the gist of this is, and what I talked about with that apples example earlier, is you have an assumption, right? You have an assumption. If I assume that if I roll a die 600 times, that I'd get around 100 2s. And then you actually do it, and you get 162s. Like, hey, wait a minute, that's way off of what I expected. So that, and if something is way off of what you expected, if something is unlikely to occur based on your expectations, then they call that result statistically significant. So again, the thing with the apples, that example with the apples earlier, the farmer expected 100 gram average mass. All right, but he took a sample of 150 and got 98. Now, in that particular experiment, that was considered far off. That was considered far off of his expectation, so statistically significant. Right? You have an assumption. You take a sample. You run an experiment, and if the results of that experiment are significantly far away from what you expect, that's statistically significant or unlikely to occur, right? If measurements or observations in a statistical experiment are unlikely to have occurred by chance, statistically significant results. All right, and they read through another example here, which I'll let you read through these examples as well. And they talk about significance level here. So if they mention a particular level of significance, that just means the probability of things occurring are less than that number. Right? So if, like I mentioned, this was mentioned earlier, if the probability of an observed result occurring by chance is 1% or less, then the difference is statistically significant at the 1% level. And if it's 5% or less, that would be at the 5% level. It all depends. You'll see a lot later. We'll see in a much later chapter that concept of statistical significance or level of significance come up. And they read through another example here. Right, so I've got probably another example here. All right, so a recent survey was conducted to determine if political party has an impact on whether a person believes that higher education is necessary for career advancement. In the survey, 410 Republicans and 409 Democrats were surveyed. Of the Republicans, 36% believed that higher education was necessary for people to advance their career. This is very different from the 65% of Democrats surveyed who stated that higher education was necessary. The calculations were statistically significant at the 1% level of significance. So that just means, right, because again, what the researchers are, what you would expect. See how these groups are about the same size, the group of Republicans and the group of Democrats? You would expect, if you take two groups of the same size, that their survey results would be similar, right? But you actually do it and see, oh, they're way different. And they're saying at the 1% level. So they're saying that the probability of this happening is less than or equal to 1%. So the chances of this happening are unlikely, meaning that I would not, meaning that the percentage of people, Republicans who say higher education is important is going to be different than, in general, it seems from this sample, than the percentage of Democrats that feel the same way. Right. So at the 1% level of significance, political party is associated with whether a person believes education is necessary for career advancement. Right, it seems that way. It doesn't seem there is no. It doesn't look like there's no difference. It looks like there is a difference based on political party. Political party does have an effect. All right. Political party determines whether a person believes. What's the difference between these two statements? Because these are both at the 1% significance level. All right, so this one's political party is associated with whether a person believes that higher education is necessary for career advancement. This one states political party determines whether a person believes that higher education is necessary for their advancement. I don't know if it determines whether or not. I believe it's just associated with, like you see the people's parties and then their opinions. All right, so I'm just going to submit what I have right now. Looks good. All right, cool. All right, we just got one more objective. Sorry, I'm not going to worry about how long these are anymore. I'm just going to do all the ones I can, and you can flip through these videos as you like and use them as guides. All right. Now this is use conditional probability notation to describe events. Now conditional probability, I'll go to more instruction. All right, so conditional is a, when you hear the word conditional, a conditional statement is if this, then that. All right, if this, then that. So a conditional probability is if this occurs, then what's the probability of that occurring? Right, it's the probability of an event occurring if another event has already happened, right, or given that another event has already happened. So the word given tells us what we'll be calculating, that we will be calculating a conditional probability. Right. So the conditional probability of A given B. All right, this is the probability of A occurring given that B has already occurred. All right, it's the probability that A occurs when, if B already occurs, right? If then. If B occurs, then what's the probability of A occurring? All the same thing. It is written this way. The probability of A with a little bar in between them and then B after. This is the probability of event A occurring given that event B has already occurred. All right. So they read through an example here. I'll just go to a problem. All right, you can read through these examples. I'll just go to a problem. All right, so here, let E be the event that a randomly chosen voter supports an education bill. All right, so E means a voter supports the bill. Let C be the event that a randomly chosen voter has young children. So identify the answer which expresses the following with correct notation. So of all the voters who support an education bill, the probability that a randomly chosen voter has young children. So these are the people who already support the bill. Right? So event E has already happened. Right? So this is all the voters who support an education bill. So I'm only looking at, so event E has already happened. We're looking at people that we know support this bill. Then we're asking, what's the probability that they have children? So that's this statement here. It's the probability of having young children given that you support the education bill. Right. Hopefully that made sense. Right. Conditional probability. If you already know an event has happened, and then you want to find the probability of another event, that's going to be typically written in this conditional notation. The probability of C bar E, C given E. Right. So another one like this. So they have you filling in the blank here with letters. So let R be the event that a randomly chosen person lives in the city of Raleigh. Let O be the event that a randomly chosen person is over 50 years old. Place the correct event in each response box below. All right. So, given that the person lives in Raleigh, the probability of a randomly chosen person is over 50 years old. So look at the word given here. The person lives in Raleigh. So that one is already happening. So that goes after the bar. All right. The event after the bar in this conditional probability, this is the event that has already occurred. We already know this. The person lives in Raleigh. And then before the bar is the probability we're trying to calculate. All right, what's the probability that a person who lives in Raleigh already is over 50? So that's where the O would go. So it's what the probability of O given R. The probability that a person chosen is over 50 given that they live in Raleigh. All right. Again, they go through the explanation and all that here. All right. So again, this is very similar. So it says, of all the cancer patients that have received chemotherapy, which means C has occurred, they have received chemotherapy. What's the probability that they have had elective surgery? That's event E. So what's the probability of event E given that C has occurred? I think I got one or two more here. So it says the probability that a randomly chosen voter is a woman given that the voter supports the president. So that's W given S, right, if you read through that. Right. And that's it. Okay. So again, hopefully you can use this as a guide when you go through the assignment on your own. And as I've been saying, please read the OpenStax book, look at videos I've posted, look at more instruction whenever you come across an objective you're not comfortable with. Look through this video here. You can flip around, see when I'm working on certain kinds of problems, and hopefully it was informative. Hopefully it helps you out. All right, and thanks for watching. Let me know if you have any questions, of course, and take care.